Yeah, so I chose to give this lecture that is sort of optional about the intentional agent, as it makes several interesting points. But the one interesting point that we have just recently made public, this is actually based on Jan Tekulve's doctoral dissertation, which was finished like maybe, it's actually no longer in press, this paper is out. It's about, was finished maybe 2 years ago, but until it was published, took some time. And in the meantime, is in industry, as we say, left academia. And so in the end, there's a lot of stuff here, a lot of things that are more to create the impression how complex one can get. And there's going to be one real insight. I'll make you aware of that one insight here. And so one way of presenting that is to say the things that we've learned so far, what's their reach? Is it, we have these models, these different phenomena, but is that how does that reach the mind? It will make a theory of the mind. Those who are in cognitive science heard my lecture on different theories, and I was talking a little bit about what it means to understand the mind, so connecting to that. What would it take to understand the laws of the mind, right? And so it's difficult to address just like that, you imagine. So what we did is we took concepts from philosophy, from the philosophy of mind, to explore that somewhat systematically. And that's essentially the concept of intentionality. I'll explain that in a moment. And the notion of direction of fit, which turned out to be, that led to some kind of insight, which I will show. We also use the notion of psychological modes, which I explained, which is not as rigorously grounded in the philosophy of mind. It was more or less an ad hoc classification, but will be inspired by that. So let me define these terms briefly. You will see that it's inspired by the philosophy of mind, but it's actually used in quite a different spirit. And when I actually presented this work to John Searle, and he was only mildly interested because it's a very different mentality that we have about it. So intentionality is defined by philosophers as the capacity of organisms, humans, animals, and so on, to generate mental states that are about things in the world. It's also usually what we, neurally inspired theoreticians call representing something, but philosophers have much more subtle distinctions here. And so that it's important that the things will include the organism's own body. And in fact, we will see that it's meaningful to also even include states of the nervous system of that organism. And that's a point I don't think that is being appreciated enough. And now that's a little bit abstract. Notion has its own history of thought. I always refer to John Searle, who published very much about that, and he formed some of the more concrete concepts we'll be using, but it goes back to Breton apparently and older people. So this is a notion of intentionality that's a little bit different from our intuitive notion of when you say, I have the intention to go to the bathroom. That's a different notion. And the so-called direction of fit of intentional states makes that clear. So there's one direction of fit that's called the world to mind direction of fit, where you say the intentional state is about something about the world, and it will be realized, satisfied. The condition of satisfaction is the term used. I referred to that last week. It will be this intention will be have become realized if the world matches the thing that I want it to be. So if I want to go to the bathroom, and then I am actually in the bathroom because I did some actions for that, then that intention has been satisfied and I achieved that. So we sometimes loosely call that the motor or action flavor of intentionality. And that's what, of course, usually people mean when they talk about intentional states in daily life. The philosophers also consider the other direction of fit, namely mind to world direction of fit, which means that is an intentional state that's about the world, and it is satisfied if the mind matches the world. And that's what we call that sometimes perceptual. If you have a percept, then something in your mind corresponds to what's out in the world. And that's very often by neural network modelers and psychologists, connections and so on, is what they mean by representation. So there's something out there, and then there's some activity in your network, and that activity represents that thing out there. And by that, they mean some kind of non-trivial relationship where maybe out there, you have an image, for instance, on your retina or a little sequence of images, and some activation comes about in your mind, your nervous system, that represents an object in the world, right? You don't directly append the object, you're actually having some sensory interface with that, which is reduced from just a 2D image of a 3D object. If you then can somehow represent a 3D object, that's an achievement, right? And so from that point of view, they call that representation. And so at least you can see there is something there that's not trivial. And philosophers also call that a form of intentionality for something is about the world, and it's the direction of fit that tells it apart from these ordinary intentions. We call it sometimes, to make it easier, I sometimes call it perceptual flavor. I forever keep confusing also the terms, mind to world, or to mind. Think about them more. So we're using these two notions, and we combine that with 6 psychological modes that Searle postulates. And again, this is not actually based on a very deep analysis. It's some kind of survey, and we'll give it a particular flavor. There's a notion that there would be 3 categorically different psychological modes in the 2 directions of fit. So for instance, mind to world is perception, as I was just hinting at, but would also be potentially memory, when you have something in your mind, that points to or refers to something that you experienced in the past, and belief, which is, we usually say knowledge. So if you know that the president of the United States is not Trump, for instance, then that is a inner state that is about a state of affairs, and it would be at a higher level of abstraction. You don't have to remember exactly how you learned about it. Wouldn't be in that sense, for instance, episodic knowledge or memory. It was more abstract conceptual. In the world to mind direction of fit, he has somewhat idiosyncratic terms. I'll translate them into conventional terms in a moment. He calls intention in action being an actual action. When you do a motor action, you do something motor-like. And prior intention would be when you have that intention to do it, but you're not yet engaged in doing it. We would usually call that planning. Plan for it. And then he calls desire the notion that you want to achieve some outcome, that you we always call that goals. Some goals and everything like motivations on would fall in here. And so we like these terms because they do connect nicely to the sensory motor grounding of cognition. See, this is quite different than talking about computation, manipulation of symbols. That sense lends itself to grounding more. So for instance, if you think of mind to world intentions, so these perception-like intentions, that would, of course, entail perception itself, but it would also perhaps emphasize active perception, where you're directing your sensory apparatus at particular things. Working memory is actually a form of perception in that perspective. We also think of it that way. Attention selection would be of that nature. And we're learning today something about that, some subtlety about that. Is that really in this mind to world direction of it? Is it really that there's a process that brings about something in your mind that is about the world? There's the simple feed-forward picture of perception would suggest that, but I'll make that a bit more problematic. Memory, would be typically scene or event memory, loosely referred to as episodic memory sometimes. And then this belief domain is, all knowledge, all forms of knowledge that are the basis of communication and that have been learned from experience and so on. So this also entails background knowledge, and this is something subtle. When we interpret Searle, we actually look into that. One could make distinctions between something being truly intentional and something being just the process requirement in order to create such intentional states. So where you don't actually have an explicit state of the mind about the world. So for instance, the fact that the neural networks are arranged in a certain way so that we then see shape, for instance, you could say, well, that is background knowledge or some implicit knowledge about the world that we know you have to process things this way in order to extract shape from shading, let's say. But then in a deeper sense, this would not be really a form of intentionality. That's just the process support for that background skill. So that's not what I call background knowledge. Background knowledge might be knowledge that you don't necessarily can articulate, but that is specific, that you can, that is not just the processing. That's a detail we don't need to go into. And then in the more conventional notion of intention, the world to mind, you have the motor control, you have plans, action plans, every action series, sequences, as I was arguing last week, which entails thus also decisions that occur in that sequences of actions. And everything about goals and motivations, and that's where emotions would plug in. They would be one form of support of selecting goals and selecting motivations. So here I've put the little translation terms behind it, somewhat mysterious terms. So knowledge for beliefs and goals for desires and plans for prior intentions and action for intention and action or motor behavior. So in the particular way we fill this, we actually distinguish between grounded and propositional forms of intentionality. So grounded will be the ones that really make direct sensory or motor contact with the sensory motor surfaces. So for instance, our fields, feature fields, color over space. And then on the motor side, we didn't talk so much about that, but if you have some like a movement direction for your hand that somehow is directly connected to the muscles, that will be a grounded representation. And these grounded representations will typically be continuous. You have continuously different retinal locations, continuously different colors you can perceive, and continuously different movement directions. So they relate to neural fields in our language, and fields that are where the dimensions come from the coupling structure they have to the surround, while propositional would be ultimately categorical names for certain types of objects and so on. And they will also, as you know from this lecture on nested structures, you can see that they can have this more complicated forms of binding. So they are more flexible and have additional properties there, which I'm not elaborating here. And so we will be looking at propositional forms of neural activity in the belief and desire domain, actually very weakly in the desire domain here so far. And then actually it's both happens at the level of plans, of prior intentions, and of memory. And again, what this model is actually very limited there. It's just, it has a real system for beliefs. It's just as a exercise, and the others are not right down here.
Like this continuous states as opposed to maybe time steps, I guess. And I was just wondering what exactly it meant for the grounded states to be continuous, and why exactly they are continuous and the propositional ones don't have that property.
So when you so let's address that, because I want it to be really down to earth, very simple. And so in the perception domain, for instance, you could have a line, that is oriented in different ways. And I'm not talking about time, I'm talking about a continuous parameter. So for instance, you could have continuously many orientations in which you can see that. Of course, if I ask you to estimate it, you make some error and there's some resolution, but it's not like your perception of orientations lies on a grid that you only can do certain discrete. Yes, yeah. Or your position is like that. And if you look at shapes, you could deform the shapes, right? They could be around. So they always span continua. And similar for actions, you can make movements in different directions with different speeds, and you could continuously vary them. That makes demands. So for a neural system to do that, it needs stuff. Some of you saw my Breitenberg lecture with just two sensors, and you can see it's maybe that does something, and it is able to go in continuously many directions. But if you were to, for instance, try to form a memory of which directions you went to, it would be not so obvious how to do that. And you would ultimately say you need a lot of neurons to represent all the different options, even in a way that it's not on a grid, that you could sort of interpolate. And that's where the fields come in. Right? The fields are essentially interpolating and thus creating the continua. So that's the expensive part that's often being overlooked When people think of neurons as discrete things and think, oh, that's what's essential in neural networks, but that is actually a misunderstanding. They span continuous stuff, and the fields are exactly how we do that. Categorical would be a lot of concepts, right? You know what a bottle is, and what a chair is, and a table is, and you know different animals by name, and the capacity to refer to them as categories means that you think that chairs are categorically different from tables. Doesn't mean that if you have to judge a picture on with respect to whether it's a chair or a table, you couldn't create some ambiguous figures where you would have to worry about that, or let's say male, female, or there's some of these drawings which have multiple interpretations, right? And you could sort of try to make that a problem, but then actually your behavior is to switch to either say this or that, and there's hysteresis, so you can see that switching actually tend to stay in one solution versus another. So that's what I would call categorical. And so the non-trivial hypothesis is that it's the categorical representations that are the basis for propositions. So propositions are essentially strings of such categories that have relationships that are quite flexible, where I can say the red chair versus the red table versus the red hair of some person. And thus I can combine. So supposedly I can combine red with a new object category I just invented, and you never saw an exemplar of that, but you can already attach red to that object, let's say. That is the property of what I call loosely propositions or language-like stuff. It doesn't have to actually be language, it could be just conceptual. And like you can in your mind construct. I always take this example of the cover of a pen, and it has this thing here attached, and I don't even know the English word for it. Actually, I might be able to figure out the German. I don't recall, but it's a concept that you can actually work with, and you could think about it and have some properties and link it to some things and so on. And so that shows that it's a conceptual thing, and language is sitting on top of that. Yeah, that's what I call propositional. And in a way, intuitively, people think that's cheap. The early way that connection is that in a network, one node was standing for bird, another node for feathers, and I say if they are activated, then it expresses that birds have feathers and so on. And of course, that was in a way cheating, because they didn't really deal with how you take a piece of video and then activate that node for bird, which is actually a major problem, right? And now somewhat solved with the modern deep networks, but it is still a question of how biological that is and so on. So the nodes of neural networks don't really say anything about whether the underlying representation are continuous or categorical. But in dynamic field theory, we really invest into making that clear. So we build the continuous representation with the fields. The nodes as such are not complicated to build, but how to give them these properties that they can have flexible links, which we call the binding mechanism, right? That's sort of achieved. So that's the larger question for that, answer to that. Yeah, good. Good. So here's this example. So I'll take you through an example. We took forever to design this example. We still made one really stupid mistake, but not very problematic. Actually, Helena is now working on a new variant that does something maybe less arbitrary than this one here. And you will see, even though this example is very simple and stupid, it is a lot of infrastructure that's needed to get this right. So this is an agent that's supposed to have intention states in the 6 psychological modes, the 2 directions of fit. And it's in simulation, but it's really simulated with an actual sensor model and so on. So it's a little agent. It's in webbots. We could just grab this. This is the KUKA vehicle, but our vehicle actually only moves along a line in front of these objects. It has an arm, and actually it's also a KUKA arm, but we don't deal with we use conventional stuff to compute the joint angle. So we're really thinking about the tool here, and it can move in space, and it can move the arm, and it can do 2 actions, which is painting and picking up paint. And these actions are just symbolic. In webbots, you can sort of send a state like paint or pick up paint without doing the motor control of that. It has a vision sensor, so a camera, which you see here, the camera, I don't even know, it's supposed to be here, I guess. This is the image it currently has when it's positioned this way. And that's interesting to us to see the coordinate frame issues. It only has a local view, it doesn't see the whole scene. And it has perceptive sensors, that is, it knows where its arm is and its whether it has paint in its inner reservoir or not, and stuff like that. In fact, we also assume it can do dead reckoning, kind of estimate where it is based on how many steps it makes. The environment consists just of objects of two types. That's where we made a stupid mistake. They're all colored, and the tall ones are the paint buckets from which you pick up paint, and the small ones are the ones that you would paint. It would make much more sense to do it the other way around. Like they have a small paint bucket, but that's enough to paint a big object. But somehow when Jan coded this, we did it this way, and then it was too late. We had so many pictures that we didn't want to redo that, right? So very unintuitively, the paint buckets where you pick up something are the big things, and the canvases that you paint are small. And in a moment you'll see what this painting task is about. So in perception, it can see colors and can see this height feature. We're just extracting it in the image how many pixels are, like in this robot I talked about last week. And the sensors for arm and so on, that is just from webbots that we get the state variables, right? So it's not really physiologically modeled. It has, and based on that, it will create, essentially analyze an image like that. I'll show you that in a moment. And then it has sort of actual actions, move in 1D. And actually, we do it very sophisticated. It can move like in a given time. Overkill. We didn't even need it in the end, but it will do like a movement of a robot arm. So it's a nice profile in time, total overkill. And you can actually do that also with the arm. So also nice velocity profile. And then you can essentially switch the neurons to apply paint or pick up paint. The memory is essentially a scene memory. So it creates a memory of the scene based on its local view. So it's not trivial because it does actually have to integrate that from different coordinate systems, because in the world, scene memory in the world. And so it does what we once looked at back in the lecture. So I do this because it takes a lot of the stuff that you've seen. So I taught you about how you assemble memory by taking each item, the different feature values of each item. It essentially does that because it has to transform them based on its estimate where it's in the world. This prior intention means the kind of action sequences that we give it. These are pre-programmed and designed sequences. So it can search for a paint bucket. It can search for, search in order. So searches for a canvas, sorry, in order to paint, or it can search for a paint bucket in order to load paint up. It can do the paint. So it's also a sequence of things, and it can move to a location that it recalls from memory. And so it's a whole sequence of recalling it from memory and so on. I'll show you that in a moment. And then the big thing is that we have these propositional beliefs. So this is the thing that we organize this around. So it learns painting rules, which we arbitrarily invented. So here, when you apply pink to blue, you get yellow, let's say. So we made up some rules like that. So it's not normal color painting rules. And these rules are beliefs the system has to learn. And we're looking at how it activates these beliefs. So when it wants to get a cube to be yellow, it might know, oh, I can get yellow if I take a pink one and apply blue, and then it will look for a pink one and for a blue paint bucket and do that sequence, right? That's how we try to create this notion that it uses experience to achieve goals. The goals or desires are trivial. It's really just to paint cubes in basic colors. So it has the goal to paint something yellow. It's just a fixed goal. And all the system does is achieve that goal, and then we're done. And we're interested in Helena. Actually, Helena is just visiting us today. She's does an internship in our lab, and she's actually doing a project where we will look at being more flexible about goals, having maybe different goals that you can switch between. Good. So that's the structure of this. This is the architecture that's underlying that, and it doesn't show everything here. So I mean, maybe intuitive, that's not totally trivial to get this right. Now, I'll take you through some aspects of that architecture. Just globally, down here you see the sensory motor hardware. So here are all the motors, the wheels, and the arm, and the switches. And this is the sensor, so the vision sensor. I'll say a little bit about that in a moment. And then there is a little bit of perception here. We put this one on top for some reason. And the memory that's built, there's a lot of substructure in there. And then these are intentions and actions, so things that can be activated really while they're activated, they're loading on sensors, while there are some prior intentions that only activate other intentions that not themselves, so that represent more like whole sequences of actions. And this is the belief system I will be looking at, and the desire is just one field where there's a peak at one color. So that's the trivial part of it. So I'll first talk about mind to world intentionality, because that's sort of new. Now, last lecture, we already talked about condition of satisfaction called intentional. See, that was like pre-shaping our thinking. And these were all examples, as you may now see, of world to mind direction of it. They were achieving something in the world. Intention was achieving something in the world and then being done when that was achieved. And I'll come back to that because we have that. But now I'm talking about mind to world intentionality. So where we're trying to create a certain state in the mind that matches something in the world. And of course, perception, in a sense, is the most elementary one of that nature. And you see, when you think about that immediately, you see it's maybe has a different logic. It's input driven, we would typically think. That is, looking at something and something comes up in your mind. And so in neural network terms, it will be some input makes a peak somewhere, I would say. Now, quickly we'll see there can be top-down influence on that. And maybe you're looking for something specific, not just any peak. But at this step, just say that. And so when the intention comes about, it matches something in the world, because that's how it came about, because the information in the network is connected to something in the world that caused the intention to come about. So the condition of satisfaction is actually the same as the intention. There's no Searle, philosophers talk about logical condition of satisfaction. We're talking about process and neural activity that is the process instantiation of these concepts. In these terms, the process, the neural activity, that is the intention, that is the same as the condition of satisfaction. It thus also has the same time structure. There's the attention comes about when the activation is formed, what we call the perceptual representation is formed, and condition of satisfaction comes about at the same time. And it's lost when you forget about that and look at something else. You might have some process of interference where you're not attending to multiple things at the same time. So it has this time structure that these are co-active, and they are active as long as that intentional state exists. So here in the architecture, there's only very limited visual perception. I'll show you a few elements of that. Just want to highlight a subsystem here to get you a little bit of sense for the complexity that actually takes. So for instance, remember that we had this notion that when we perceive something, like we attend to a certain color and a certain the height is the other feature value. And that means we're looking at a particular location in the visual array, have intentionally selected it. If we want to put that into the memory, we first have to do a coordinate transform, right? Because the memory is in the world and we're currently looking somewhere. And so this T is a little coordinate transform that takes an estimate of where the robot is as a parameter to shift this space to be on that space. And then in that state, we want to enter the feature information one item at a time. And that takes some controlling through spatial attention, whether or not you enter something here. And in fact, there is a single peak where you enter this, and then it's entered in the long-term memory. This one has long-term memory because it lays down memory traces where these objects are. So you actually, it's not working memory, right? Working memory is actually, I think working memory is, where is that? Is it here? I think this might be working memory. yeah, I think this, I don't actually know where my memory is here in this model now. So that's just part of perception for us. It's input driven, and then it activation stays around, but it doesn't have this process of being reactivated. While long-term memory is something that you have to recall if you want to use it functionally. And so that's done by the memory trace up here. And when you do that, you have to explore. I mean, to build a scene memory, you have to look at everything you can currently see and then enter it into your scene memory as a sequence of things, and it's controlled by these conditional satisfaction intention nodes. You're done exploring when every object that's in the scene has been entered in the work memory. You have an inhibition of return system that will signal that now you're done. There's nothing left to be activated, and so on. So I'm not explaining that in detail, but you can imagine that to do that, you go to a new scene and now build a work memory. As a process already requires a lot of structure. And there you see it's maybe not just input driven, right? It's actually driven by some internal process. In a moment, we'll see that those processes have the opposite direction of fit. So this is the sensory surface, so it extracts a spatial salience map, and this based on the saturation of these colors. So it will know there are two locations where there is something, and it's only a 1D in it only knows the horizontal orientation of the object. So only moving along a line. We just draw these things in 2D to make it more visible. And then it has the space color map. So this is color and that is space. And then the height map. There's a not so tall and a tall object here, right? So for instance, this currently would encode that on the right, there's a tall thing. On the left, there's a not so tall thing. And then here, the color, I think the color code is not really visible here. So there's some encoding of color along this axis. So I guess here the left is not the blue, and that must be the yellow. So that's the input to the perceptual system. So here's an example. I have only, we have this material that I have in nice form, or just some simulations that are not always the best example. So here's an example of the system looking at a particular visual array. There's an object here on the left and right, and it then attentionally selects the one on the left. This is salience-based bottom up, so it doesn't have a goal here, it's just exploring. And therefore, it builds a peak on the left, and that gives a rich input into the corresponding feature field. So this is the retinal color space field. So this peak here will be activated, and the corresponding color comes from the direction of the sensor is whatever that color is. I think it refers to this moment, so it must be blue. The other one is not selected, and it is actually entered into this is the same step here. This is the color, and it is now entered to see the estimate of where the robot thinks it is somewhere that's not shown here. And that leads the robot to estimate that this object is in the world at this location. This is some other axis, it's driven somewhere. So the location that on the retina is this one corresponds to that. And that is, between those is a coordinate transform. And so in the memory, it enters that by having a ridge along color at that location in space. And then it has from the color system this ridge, and that together gives a peak. At this point, it takes a moment in time for that peak to come up. And then as that peak comes up, it lays down a memory trace. I did discuss the memory trace, didn't I? Or did I not? This was this learning lecture I did from Portugal, right? So that's our form of learning. A memory trace is like a long-term change of the resting level. So there's a memory trace being laid down in the color space field. So this is allocentric space. That's you see there are 3 objects in here now. It sees on this retina only 2 at a time, but because it does transform it, right, it can accumulate a memory of something in the world. And this here, I don't remember what that is. And so a moment later in time, it will be selecting the other one. So it deselects, and then it will be selecting the other one. This is not in the sim series. Up here, you see some of these nodes that control which behaviors on. So for instance, you see that the visual explore behavior, that's its intention. And then when it's done, when it's put everything into memory, its condition of satisfaction comes on, this one here, and then they're both, and that turns off the intention, and then they're both turned off. So that is a motor-like, right? That's the kind of intention that we discussed last week, where you have an intention until you're done, then you turn off. And in the terms I'm now using, that is a world-to-mind form of intentionality. It has that time structure of that, and the world. So what is the state in the world it intends to? It's actually the state of its of its memory. So it has a goal to create a particular state that, in fact, that's what turns this off, that it has seen that it has put the right kind of peaks into this memory and is done doing that, then it's satisfied. So this process of creating the memory representation by selecting items one at a time is actually a motor type of intention. It's not input driven or forward. It doesn't have the structure that it's just active whenever it's active. Right? This is very significant. Later, I'll argue that conventional neural networks, including deep neural networks, don't have that. They only do input driven stuff. Right? They don't do this other kind of intentionality. So this other time structures, you could say top down or driven from intentions. So it's important for the subtlety. It's important, of course, that the part of the intentional, the activation. Now, if I say it's intention to achieve a particular state of activation, that state of activation is, of course, not the activation for that intention itself, right? If the explore intention had as a goal to activate the explore intention, right? That would be tautological. That wouldn't make sense, right? So you can't say I have a neural representation that is about a part of the mind, and that part of the mind is that state itself, right? That's not what we're talking about. We're talking about a other neural activation that has some other task here, the task of being memory, and your intention is about creating that, and the intention for that is, of course, a separate set of neurons. So there's just one neuron out for doing that, right? Just to make clear that there is no contradiction in having a mental state represented by neural activity that is about creating neural activity, but it's neural activity somewhere else in the brain, not the same one that represents intention to do that. Right? So there is no logical problem there. Okay, so this is just one example of that. Here's a video that shows a sequence of events like that. So it's here, this essentially what I told you, except I think it starts with the opposite. So these two objects in the selects, let's go back here. So somewhere here, it selects the right one. Yeah, here, it's the right one is selected here, the right one. This little red cube is the sigmoid of that. And then once in the exploration, and it's going too fast, sorry. So let's stop it here somewhere. And now it has selected the left one. Maybe I didn't look fast enough. Now let's go back here. Oops. So it's actually the left one that's selected first. This one here. And that one is the green one. So here is green. And in the world, it's at that location, further to the right. While the retina is on the left, right? You see it's a different coordinate frame. That's why it's here. And it is a small one, so it should be coming up somewhere here. And then this is how the the ridge input makes that come. Let's a little more. And it actually then does a check whether the color it currently attends and the color that is in memory matches. And that's the signal when that matches, the signal that it's done with creating that peak. And so now the height has been entered. And then sorry. Kind of hard to click this at the right time. It's the same happening again. And then a moment later, the right one should be selected. Now, and then it enters the second ridge here at, that's further to the right. The yellow is further to the right. It's at the far end of that allocentric frame, and then it creates an entry there. And that whole thing is a entails this visual explore intention, which is always ended when it has created the memory icon. And there is another one which is just it's looking around the scene. So I'll not say more about that. I already said this here. Now this was how the memory was created, right? Now memory being activated. I'll have that later. Yeah, I remember. That comes later. I'll show you how you recall a memory, which is actually also a world to mind directional fit. The belief is the third thing that is of the mind to world direction. This is a fairly complex story, and I'm not going to explain to you but I think I did show you that in the learning lecture, right? Didn't I show you how beliefs are learned? In one course I did that, but I'm not sure I did here. Maybe you recognize that in a moment. I didn't explain the whole context. So roughly speaking, yes, please.
About the belief field, like as a memory field, how they are coherent with each other. I don't understand this part.
Let me explain the belief concretely how we do it here, and then we can maybe say that precisely. Here, it's all very similar because it's all about color, and that is a bit confusing, but we can still say that. So the beliefs are about these color rules, right? So the beliefs are about knowing, for instance, that if we call it that would be the paint. Actually, Jan used the word code for the paint that you apply, right? Better just think of the paint, the liquid paint, and then it's on top, then it's the coat. So you talk about the coat or paint color. Let's say it's this kind of, what is that? Cyan or something like that, light blue. And then if the canvas is, oh no, this is not the active, it's actually here, this whatever, orange. And then the other color would be, I don't know, some color here, maybe it will be this node. And then the result, the outcome color would be, I don't know, also some color here, some other node here. So then this triple of these nodes is the belief. And the belief is represented by neurons, and the connections of these neurons to these nodes is the neural instantiation of these beliefs. That's at a categorical level that is, these are color concepts. And so there, I don't know how many there were, 5 or something, color concepts. And yeah.
Like these arrows, you see this one, this is working like this, right?
Yeah, so I mean, this doesn't, I have slides like that, but I don't think I have it here. So let's say after learning, this node would be connected in a actually bidirectional way to one node here, one node there, and one node here. So of all these lines, only one of those connections in case has been learned to be non-zero. Actually, this sort of learning in a single try to put it all to saturation. So it's just 0 or 1. And then so it's a triple of nodes that are bound by this belief neuron. And this is actually binding different kinds of concepts, because you could say it's color concepts all the way through here, and that's confusing. But it's in different roles, right? One would be, here's the paint. You could think of that as the agent. The other is sort of the recipient, the patient, right? The canvas. And the third is the outcome of that action. So if you think of this as the result of a paint action, then the color shows up in 3 different roles in that phrase. And that would be a proposition where you have like accusative and dative, and the painting action would be the verb.
So canvas means the color of the thing that we want to paint.
Yes, the surface.
Is the surface we want it to be like after.
Yeah, the outcome, the result.
That's
the outcome. So outcome is just defined as the thing after the action is done.
So code is just the color we need to take from the bucket.
Exactly.
Then there is this canvas. This is like the aim.
Yeah.
And then the result is what we believe is gonna happen after we.
Right, exactly. And it's learned by observing that. I'll show you a video when.
And this connection between them, between these nodes, it shows that they are connected in such a way, right? So like if we take, let's say, code red and canvas blue, then the result is green.
Yes, right. And exactly. So, and there is a belief node just to organize that. The belief node is, so when the belief node is active, that enables the nodes that are linked to it to become active. It's typically only part of them. That is, you already know, for instance, the outcome you desire, and then the belief is active, and then there's a chance for the nodes that you need for that belief can become activated, and then you're actually searching for colors like that. Or you can do the other way around. You have a green code and blue canvas, and then you can predict which will be the outcome, and you can check if that's true or not.
This one, and then the machine, like the agent sees both of them, the result also activates in this.
Yeah, so they're all bidirectional. So there are multiple ways you can use it, but the way it's used is in a sense, it's a pattern completion kind of form. That is, you have partial information and that belief is active, then you can predict the other part of the information. And so there is no unique direction which you can use it. In different contexts, we're using it in different directions. And so it's one particular architecture. You would classically think this like an association task. And so you would do this by an all-to-all neural network and so on. But those are actually not very flexible and they have a lot of promise. And so this is a more controlled way of doing it. It actually is a simplification of the so-called ART architecture of Kosberg and Carpenter, for those who know that kind of thing. And it's more complicated. I'm showing you in a moment. Now, this is propositional for two reasons. The colors are categorical concepts, and they have this role. Here, the binding is done in a somewhat ad hoc way, just different copies of those nodes. But in a more flexible system, we would actually have a more complex role, filler binding, where we would say red as a paint, red as a paint. Yes, that's correct. Or red as a canvas, or red as an outcome. This would be binding red to fillers. And then the proposition is that you have objects of different instantiations of color categories in these different roles, and they belong together, and it's the belief neuron that binds them together. Now, these are still grounded, right? So they're grounded in the sense that each of these color nodes is activated by a field, a color field, and also can bias that color field. So you can actually also use it to search, right? Like a queue. You're searching for red. If this is on, then you're getting an input to red. So this drives some downstream systems, which we'll come to, that will be looking for a red object, for instance. So in both directions. So the grounding is at this continuous level, but the learning is at the categorical level, and that really plays a role. You can imagine that if you had everything at the continuous level, it would be way more neurons that you have to learn, and it would also have less invariance properties. That is, if the red looks a little bit different because of a different angle, now you have to learn afresh the color rule, right? Because for this shade of red, I haven't learned that right yet, right? And so this is one of the ways of how the system supports generalization. Now, of course, it's very modest, the kind of generalization we have here, just for different shades of color. We didn't even explore that very much. But that's the conceptual reason why we do this in categorical terms. The other reason is the propositional structure, right? Having these roles, having the roles for a continuous representation on the sensory surface would require many fields in different roles. So inside, it's actually even more complicated because to do this learning, you have to do something like essentially know which of these neurons has already learned something. So if you don't want to unlearn, like red will show up in multiple different beliefs, and there is this catastrophic forgetting that if each time you have a red paint, let's say, involved, all the neurons that are connected to red get updated, then you have to have many instances of seeing these different combinations to then have the neurons settle for something. And the art architecture has an alternative view where you have what we call commit nodes. That is, you have a particular way of saying, I have learned something, and so I'm not learning something new. So if it doesn't match what I do, then I don't learn. And we have some fresh neurons now whose commit node hasn't yet been activated that are available for learning. So if there's no node that matches the current triple, then one of the fresh ones will be coming up and take over the learning, and then will become committed and no longer learns. So this is how you can do single shot learning. That's what this does. So if it gets a single instance of a new rule, it will store that rule, and it will never forget an old rule, which is actually very likely true for human memory, right? We're actually never forgetting anything that we ever encoded. A lot of stuff we don't encode, but something that you encode because you paid attention and you had some emotional value, you don't forget it, it just becomes harder to activate it. And so this is sort of consistent with that kind of logic.
Really? This is inbound against.
Well, it's an interpretation of research that is the case, yeah, that you're not really forgetting. Yeah, there is some debate about that. There's this whole research group here on extinction learning. And so extinction learning is some kind of forgetting that certain kind of rules don't work anymore, and I'm also learning that. But actually, deep down, what you're learning is you still have the memory, but you know that it's not, you shouldn't activate it. So yeah. So for instance, the source of this kind of evidence is that when you have forgotten about a rule because it never really occurred again, this is all in conditioning, right, where you get reward for something. Then if it done very much later does happen again, you relearn it much more quickly. And there's also negative effects like that. If you forgot about it, I mean, you unlearn it for a while, then there can be resistance and interference. Yes, right. Yeah, right. So the other thing that might be more relevant to daily life is the habits. Habits are sort of highly automatic skills or stimulus response.
That's probably not true for facts. I definitely forgot a lot of stuff I learned in school, right?
Yeah. It's an issue. So you probably did not learn a lot of that ever. And there might be some stuff that you have that would require some extra work to activate. Yeah, I mean, this is it's the first approximation I'm saying. I'm very interested in the Zeigarnik effect. Some of you might have heard about that. Were you, Helena, at our DFT community meeting? Maybe you weren't. Yeah. And yeah, it leads too far. But there is some interesting things. So there are things that you can somehow delete if you're done with it. But yeah. So it's a very global statement I'm saying. So here we're just making sure that, so if you have single shot learning, it will be, that is, if you then have also single shot forgetting, then it would be totally useless, right? Yeah. So so I'm not going to explain the details of the learning. It's a whole paper in IEEE. So there's a lot of subtlety in here. Just this link to reward. So there is a reward here. We call it reward. It's just an internal signal that measures that certain things are the case. So for instance, only when all the three nodes are active is there a learning opportunity. So you will not try to change these weights when just one or two of those nodes are active. And there's also a representation of whether there is an event happening here when you've seen the video when a cube changes color, and we're detecting that change. And that is necessary input into the reward signal. So only when that happens will you be predisposed to learn. In fact, the reward signal is timed. It is on for a certain amount of time, which here it learns to saturation, so here it doesn't matter. But you can imagine that if you have a learning that is sensitive to frequency, where you're essentially predicting the probability of something, then and everything is time continuous in the brain, you have to somehow make sure that the amount of learning is controlled, that you learn this much this time, and then again something else another time. And that's essentially this reward systems also comes the eligibility trace in other models that controls that. It's that, so the precondition and so what that does is that actually modulates the learning rate. So the learning rate is non-zero only when the reward signal is present. And that is actually the role of reinforcement, very likely. It is sort of a modulator of learning. So in more molecular kind of models that take computational neuroscience kind of models, they all think of the Hebbian rule being modulated by a reward signal. So you're only learning when that's the case. In reinforcement learning, this is an abuse to encode the goal of the learning, the information about what to learn in the reward signal, which I think is totally misleading. In the brain or mind, the goal of the learning is intrinsic. You're set up to learn certain kind of things, to be interested in certain outcomes. And so it's nobody informing you about the goal of the world by giving rewards, because the reward is intrinsic. Anyway, that's another debate. So let me just show you here this one simulation. So here, all the belief nodes, I think this is the case where none of the nodes has learned anything. All the weights are zero. So these are the belief nodes. These are the weights with which they're connected to these color, actually to the color concepts, and then the concepts aren't shown here. It's just the fields that are shown. This is when the change detection occurs. You pay attention to this cube, which I think will still change color. Yeah, it will change color in a moment. This is what the robot currently actually sees. And when it changes color and it takes over some processing, then the reward node will go on and will start learning. It will select one of those nodes. I think it's the leftmost by default, because it's all fresh. So just by chance, it connects one of those. So yeah, did you see the color change here? Yeah. And so the detector went on. It now has the three things loaded here. So the three nodes are active, and that will ultimately boost the belief nodes. And this one is activated, and then the connection from that one to all the different color concepts, or they're listed here, the color concept. Those, now it has learned that, I don't know, I can't read that, but certain color combination showed up. I think was the outcome. So purple, yeah, it's the outcome. And before that, it was yellow, I think, right? And the color applied, I don't know. So the canvas must be yellow. Is it yellow? Yeah, yellow. This is yellow. So it represented yellow with something applied that we don't see here gives pink. Yes.
Like we're actually acting, or if it's like just passively proceeding, we're just seeing the colors change.
That's a good question. So it is learning from experience. It's always trying. There is an exploration of it trying. So it is, this is in a sequence of actions where it's taken some paint and it's applied it to some canvas and observes the outcome. It's always doing that. And it's also some organization of how it spends its time on what, which I'm not explaining. So it's always based on its own action.
Okay.
Yeah.
Also, when like with the desire in mind to paint in a specific color, so like in order to paint in this color, it first has to learn which color like makes which color, or is it just like the learning part and then the desire something and it has to be done?
That's a good question. Actually, I don't remember now if we had a separate mode, but I think we had a mode where it was just trying stuff. I think that's true. I don't remember now off the top of my head. We even when it has a fixed desire, we randomly made that the rules are not always the same. So there's some sometimes you try something that it had a prediction about, but it doesn't turn out to be that case, and it learns a new one then, and so then you can use that. It's possible that we only did it that way. I don't remember now.
So what was happening here? So first, the model perceived a certain color, like cold color, and then it started to try out some actions, and then it perceived a new color, and that's when they got this peak, right? So that was like a
Yes,
canvas color, and then what?
and the outcome color is
Oh,
it represents. So when it sets the change, has also a representation of what the new color is.
this is the result.
That's the result color. Yeah, outcome would be the more conventional term. So this is a micro example, but the concept is actually generalized now. For instance, in this new work, we're not using color for everything. You're doing certain actions, you get outcomes of a different nature. You hear a sound or something happens. In the real world, outcome would be some perception. For instance, let's say the more common thing, a little kid like my granddaughter plays with a toy and then finds out that if I press this button, this light comes on, right? And that button, something else happens. There are these kind of toys, and that's a triple like that because you have the target object has certain perceptual features. Sometimes you have actually also different actions. You can press it or turn it or do something else with it, and the outcome is what is caused by your action, which is just defined by it being aligned in time, arriving after action. And then we will do that. We did an experiment like that many years ago. I might have mentioned that it was about imitation and perseveration. So we did expose toddlers to toys like that and demonstrated actions, and they would imitate the action and observe the outcome. That's when we saw that the outcome dimension was really important. I didn't do the NLP here, right? Or did I do? I don't remember. NLP experiment? No. So there's a whole line of work that I didn't. I used to sometimes teach about it in development, where you can look at infants. Actually, it connects to things like that, where they have intentions and they persist in those, and you can initially guide them by demonstrating something, but then they will not always follow you. So if you demonstrate something else, they might still do the old thing. That's called perseveration. We all do that in some sense, and what that experiment showed is that the perseveration is about the outcome. So for instance, if you demonstrate this action and they do the action, and now you're giving them the toy. So we actually had a copy of the toy that looked the same, but on which some things didn't work. So when you press there, nothing happened. And then they will tend to perseverate. But then when that doesn't work, so no outcome, then they switch. So that so it shows that what actually drives action is this outcome expectation, not so much the action itself. This would be very much what the system actually also does. It makes a new rule and abandons the old rule. Yeah.
There are two ways to get in goal, for example. So to maybe some
Exactly. Yes.
can learn both of them, and we have two belief nodes. And if I'm asking to pick, so which one he or they was selected.
Yeah, so this model didn't address that. It would just randomly activate one, but there's an intermediate model that's actually what Elena is supposed to push further, that Stefan Sehring did in his master thesis, where we had what we call opportunistic activation. That is, you would be activating the belief for which there is some support. Like if you have a belief about pink objects and about blue, and there's a pink object in the scene, then you would activate that belief because it enables you to act now. And that is actually a thought that would generalize, that you would even activate goals. Because in reality, we have not just one goal, we have many, many goals. In fact, you often have goals, like all of you have a goal to get a master degree, I guess, but it's not the only goal that you have in mind, right? In between, you have to do other things. And so the notion would be that you're always sort of, goals are competing for activation, and the goals that you activate are the ones that you can act on. Sometimes maybe also you can't, it turns out, but you thought you could. And then there must be some memory representation of that goal being activatable. Maybe you have also the goal to become a superstar, but maybe that goal is not activated as often. No, that would be still thought. So we're interested in pushing it further in this direction. It's this program of reaching. See, this is something that is not part of most modern connections and neural network models, transformer models and so on. They don't have anything like that. No, so that's why it's maybe. I come back to that. Okay, I think I have not more about the belief learning here. Yeah, I think I did a little lecture on it. It sounds important. Okay, good. Now the other ones are the word-to-mind intentions are the ones that you're familiar with, right? The ones where I have an intention until the condition of satisfaction arises. And so the motor ones are like that. I think I have in here this here. It just show you the complexity of even a trivial thing like that, right? So for instance, this is a mix of actions where one is to drive to a particular location that has its own complicated structure here. I was mentioning that has a timer. I didn't actually discuss that. When you make an action in the world, it takes a finite amount of time, and the motor system is essentially creating time structure out of nothing, right? You can be nothing, raise your arm, right? And this neural activity doesn't arise from some input, it arises from within the nervous system. Now, this is also something that pretty much all conventional neural networks don't do. Right? They only do something if you give them an input and they translate it into some activity. And so this is, it's called an active transit. It's a system, two-layer system that does this sort of time course generation has to be turned on and off. Yes, please.
Model generated.
Yes.
Because it has this internal activation which peaks at some point and then it doesn't.
Yeah, it's of course it's in the sequence generation sense, yeah, one peak and the next peak, and when it's done with the previous peak, then there's a competition of peaks and one comes up, and there are elements in there where it's just not just a peak coming up, but it's a real time course, peak coming up and going down. It's an oscillator, but it makes only one cycle. It turns itself off after one cycle, and that is what makes the time course of the movement. So there's a distinction between making a peak, which also takes a finite amount of time, but there the time course is really just a transient to that, and generating activation that goes up and down with a well-defined time course. For instance, to make this movement like this, first it's very fast, first very slow. I need different time courses, and therefore the time course itself is an attractor. I didn't explain that here, but it's generalized this notion of a peak attractor to essentially an active transient, a time course and attractor. So those who know dynamics, we just had a seminar about that this morning. This would be a limit cycle, and what we have is a fixed point. But this goes a little bit too far. I'm just hinting at further stuff that happens, right? I'm happy to discuss it. It's actually, in the summer semester, I teach a little bit about that, yeah, but I don't say you have to take the whole course just for that. So it has this sort of stuff in here. And then recall would be activating the memory of where you want to go based on a cue, which would be here, that the color, for instance, or the category of the object. So if you know which color you're looking for, you can look up in your working memory where there was an object like that. It's just a cute selection, as the ridge, right? Remember how to do that. And that's the recall behavior, and that is mind to world, world to mind. It's a motor kind of behavior, even though it is recalling a memory. Right? So what it aims at is to get a neural activation pattern in your brain that's of a spatial location where that color is. And when you're done making that activation, you are done with recall, and then you can move there. So if you try to recall, where did I park my car? You're done when you have the neural activation in your brain where your car is, and then you walk to your car. And so recalling where your car is a motor intention of that nature. It might take different amounts of time. Huh? If you have trouble recalling because maybe you parked differently than you thought. Yes.
like remember on his birthday or something?
Yeah, so whenever you are actually trying to create a particular state of mind, you're doing an action. Yeah, so I'm actually claiming as a slide later that all thinking is world to mind direction of it. So it's action. You know? Thinking is like action. And this is not just this talk, it means it has that temporal structure that you have an intention and then something happens and you have the conditional satisfaction that turns off the intention. Then you can do the next thought. So it's actually really not input-driven neural network activation where, you know, inputs always drive the next thing, which has this other structure, right? That the input creates the activation and then some other input creates some other activation or condition of satisfaction. Yeah.
Right, so then at some point it's just like, okay, so this particular thought kind of also has this external output, so this would be like what also in philosophy, like sometimes for like, or okay, in this scheme it will be intention and action. So one of these thoughts generates intention and action, and then just acting.
Right, exactly. So some of these world-to-mind intentions really move something physical in the world or you in the world. And some of them just move something in your mind, and that is not really a categorical difference. In fact, if you go into more detail, a lot of the action likes actually have some sub-layers too, right? And we're just glossing over that. So how direct you are to the muscles might really depend. And you can sometimes replace muscle. You can replace, a lot of experiments replace an actual action by you just pressing a button and then some system does it. You know, you may know that there is this anticipatory, and you know this. For instance, if you're holding a weight, right, and then you're releasing it, there will be, if the weight is here in front, then you will be falling back, right? And there is a so-called anticipatory postural adjustments where unconsciously or automatically you're activating certain muscles on your trunk to anticipate that there will be this postural adjustment. And so that's something naturally you hold a weight on a, you know, on a pulley, you release, you anticipate correctly, or you drop a weight. Turns out you can also do this by just clicking a button that releases the weight, which is sort of, you know, mounted in some way through a magnet or something. You can also do that. You need some training to know that that's the action that happens. Okay, so this is just an example to show that this works. And this, I don't know, this just shows that something happens. So usually I just show this to say that this sequence of things is also just the dynamics doing that, right? It's not that there is a piece of code that does one thing and then it's ending. You know? Almost all demos of neural networks that drive robots, reinforcement learning, they are actually only input-output devices. And when they have the output, they call an algorithm that calls a policy. You know, they have an internal representation of all the weights, and then they call a policy, and the policy is some program, and the robot does something. Now, it's not the neurons that drive the robot or the sequence generated from the robot. So that's why you will see videos much better than this, like cars racing, you know, like a racing car driven by neural networks, right? The autonomous driving. But that's not the neural network that does it. The neural network is really just doing the input-output, and everything else is algorithms that are typically probabilistic. Now they have some functions, and they pick a choice based on that function, the most likely, you know, maximum likelihood, or one thing like that. So that's the best policy. That's the best predictor. And then to do that, they just call a function in the program, right? Drive 5 meters. You know? It's not in that sense autonomously done by a neural network, right? This is totally swept under the rug, right? So the neural network part doesn't do any actions, doesn't have that whole structure. All right. So yeah, I'm just stating that. And here's an example. I just want to show you that we're using all these sequence things. So this is a chaining, right? We have some cases where we have fixed a sequence of events. So I don't remember exactly that. In the painting action activates all of those, and that you first collect and then apply. Now, it makes sense that you're not trying to apply paint before you even have loaded the paint into your painting John. So that is a sequence that ultimately would have to be learned, right? So for instance, small children will learn to reach and grasp, and did some modeling on data about that. So very small children actually sometimes don't manage this temporal organization. So they will not open their hand before they reach the target. They might hit the target like this and then open, or they close the hand and then open it. So this takes a while for them to get this right. And so there will be like assuming that you're learning these kind of structures to do that. Yeah, the spray action is not so important. This was the recall and drive. So I'm trying to draw your attention to the temporal order here. I don't remember the colors. Let me try to see this. I think the yeah, here it's here at the end. So the green is the intention to drive, and then the condition of satisfaction comes up. The green intention goes down, and then the condition of satisfaction goes down. Now, this would be this example of self-terminating of an action when it's finally done. That's all I'm showing about this one. Yeah, good. This is a subcase of that. So here it's recalling from memory. It has already all these options in memory. It's recalling the one that is the, I think, the tall pink thing, which it has in memory, and then it only then when it's done that it goes in. The conditional satisfaction for going there is that the current prediction matches the predicted position. The peak goes up here, and then it ends the driving. I don't know what it's doing. I think it's actually painting here at the last moment. But earlier it was recalling from memory. Yeah? So it gets here the information about what the color and height of the thing it wants to collect paint from. It has the scene memory, and then gives the boost to the stuff that matches the cue, color and the height. And then once it has selected that, I don't remember, it somewhere it already started driving, I guess. Yeah, the drive intention comes up as soon as that's done. I don't know exactly where we see that it's done. I think it must be done here. Something comes up here. Yeah, you see the self-conditional satisfaction comes up and then goes away again because the intention goes away, and then the drive intention comes up, and this is its current position. This is the predicted position when it will be here, and so see here the moving there, and then detection. See the red thing here. Now it's done driving, and that turns off the intention to drive, and so on. Good. And this is just in the belief system when you recall a belief. So recalling a belief is like recalling a memory in a way. Here you give it a cue, you want that outcome, and all the nodes that have that outcome as a component get a little bit more activation, and then it selects. In this case, it actually just selects randomly one of those. I think it's at this stage here. Here you see three nodes have that outcome, so they get a little boost. It just selects one of those, so the optimistic would be biasing this by one of those. And Stefan, see how he did that. And you see here it just selects one, and then the corresponding predictions come, what code color and canvas you should do, and then it can go look for objects that match that belief. And so again, the process of recalling a belief is a will-to-mind form of intention, right? And it's also loosely what people call top-down, right? When you're doing top-down, it's not driven by input, right? Not driven feed-forward. Loosely speaking, top-down is often a will-to-mind direction of fit. Most people who use these terms are not really very precise about it, but ultimately it means that. And that means that you have that in a structure, because when you have top-down, then you have to find out when am I done with top-down, right? In the other cases, just the input does whatever it does. If the input is away too quickly, well, then you didn't pick it up. Like, simple. So it shoots a bullet at you, then you don't perceive it. It's too fast, and that's what it is. But with these actions, you have to allow it the right amount of time. And that's actually a real problem for desires. If you have a long-term desire, like you want to get your master degree, how do you manage to keep that active over this very long time? How do you know that you failed, right? For instance, so if you, I did last week, right, this condition of dissatisfaction, that would be that you say, I have this race, my default is to give up, and then if I'm interrupted by success, then I've have the condition of satisfaction. And that makes sense for small things, like, I try to grasp, and then if it doesn't work, it has to slow down, then, you have some expectation how long it will take. But if you do something more complex like that, how do you know when you failed? We know it's a problem, actually, a psychological problem. People are not always good at regulating how long they try. But we don't really have a good theory. It would be bizarre to think that there's a timer that goes so slowly that it knows after 2 years I should maybe start giving up. So, that's an extreme example. So there's some interesting frontier to understand how we're the economics of goals. There's some psychological work on that as well. Okay, and so the last point I want to make about this is that this is the example of achieving one desire in this architecture. It was painting something in a particular color, and this is when it's done. And so there's actually one error here, which I'll not point you to, but other than that, pretty much everything you see here. So you're seeing the windows in time when the intention is on and then the condition of satisfaction on, during condition of satisfaction ends, the previous activation. And so pretty much all you see here is word-to-mind intentions. So we found that for doing this simple behavior, almost everything is word-to-mind. And mind-to-word, it's a little bit when just visual exploration, like building a memory. Yeah, you look at that and you put it in this. There are a few things like that. But pretty much everything you do when you are goal-oriented is of that other form of intentionality. That's why it's significant that it's not something that conventional neural networks do. Yeah. So that's just the claim I made. Okay. Did I talk about the conditional satisfaction not happening last week? I did, right? Or did I not? That was my other lecture, no?
I missed the last question. I will watch last week's session. I don't know.
Because I just noticed I put those slides in here. It's not a trick question. I honestly don't remember. So let me have a quick look. Because ideally I would know that by heart, right? Condition of dissatisfaction. I did it I did it, but probably not good enough for you to actually be able to. So I'll do this very briefly again, just to set up that problem. Oh, did I share? Yeah, I think I share. Yeah. You might remember this. So if you're not successful, this is important in this architecture because it will happen here. So there are two cases. The one more technical case is that just something happens that you are not. So something happens, and it's just not exactly the right thing. And this will be, for instance, here the case if you use a color rule and then that isn't. It's not the one that you thought it was, and then you have to do something. And I'm showing that that's a kind of trivial case that you can easily catch. The more non-trivial case is sort of nothing happens that is in the kind of active representations you're making predictions about. No peak arises, nothing happens. How do you handle that? This is the absence of an event, right? For us to get anything going, we need to get some neuron to come up, and make a detection, suppress someone else. That's a condition of satisfaction. So how do you do that for other things? And this is this notion of default answer. I think now you might recognize, right? Yeah, the same detection. Essentially, what notion would be that you have some way of activating a node if nothing happens. That's the timer that predicts that the time it would take to get a response. So it is actually done in a way where the time for it to reach threshold is a control thing. We use this oscillator kind of notion, active transient. And then it can be interrupted anytime by the event, which would be the condition of satisfaction, and that would stop then the timer. So this will be the condition of dissatisfaction. I call this here. This will be the condition of dissatisfaction, the same node, and the different node would be the condition of satisfaction that can stop the answer. And so we use that kind of architecture. That structure is not exactly in this form, in this architecture. This was the other one that I said. Okay, so what do we learn from that? So the most important thing, this is the one thing that I mentioned, that this world-to-mind direction of fit is quite fundamental. It's pervasive, very fundamental for thinking and acting. And it is not something that is typically considered in neural networks. Now, almost all neural networks are input-driven. Even the recurrent ones typically are active only because they're driven, and then the recurrency does something to them. But there's always the idea that you're responding to something. Your transformer network will react to a cue you give. There's something where they take the previous result and feed it in. So it can be some kind of sequence that way, but it's typically done algorithmically here.
Some influx in my mind, or am I wrong?
No, this is actually the opposite. World-to-mind direction of fit. That is, you are having intention, and it's
So it's flux in outside.
so if you think of the flux, it is from the mind to the world. Yeah, that's why this word is a bit. It's the direction of fit in this logical sense, and so that means that the world has to fit what your mind wants. And of course, the world does that only because your mind does something to the world, right? So the flow of action is that you have this intention. See, in the time structure, you see that the intention is there, and that drives your body to do stuff. And then you see that the world has actually changed according to your wishes, intentions. And so that is this action-like direction of fit.
So to make sure that and it's fundamental in the sense that the machine, that the agent is going to work until it's satisfied. And
Yes.
it only stops doing the thing it was doing because it's satisfied now.
Yeah. And it's fundamental in the sense also that it's not just the motor stuff that's like that. That is also when you're doing any thinking, then it's the inner structure of that is like action. It's the same structure. That is, you're aiming at something, you're activating things, and you're doing that until something happens that the thought themselves already predicts. It's part of the thought that they predict what has to be the case for them to be done. If you recall from memory, it's when you've recalled from memory that you're done. That famously does take different amounts of time, depending on how easy it is activated, that memory. And so the realm of these things is much broader than you could think. It just takes the delay of getting something done in the world, that causes this, but that's not the case. It's actually all processes are like that. So in hindsight, it's actually exceptional, these cases where it's not like that, where you're really just getting the world to drive you. So mind to world direction means the flow is from the world to the mind. And you say, so that is actually quite uncommon. It's totally so even perception isn't like that at all. Almost all perception is essentially visual search. You're looking for something. So there are a few exceptions. One are alarm systems, like a sound comes on, right? And that triggers something, and the auditory system is particularly tuned to that. And there can be strong visual transients, like if a door goes on, or some major event happens, some transient happens on your sensory surface, then that will attract attention, and then you will actually do something driven by that. While it's not so common. I mean, that's the case a lot for movies and videos, and that's why they are so problematic, perhaps, because when you have video screen, you're totally passive, just looking at the video screen. Maybe you're not even doing a lot of sequence, you're just staring at it. And there's a lot of change coming. And then there's interesting stuff, we're intrinsically rewarded by activation. We're looking for stimulation. People usually say that they mean the activation in the brain that causes. And so you constantly get that. And therefore, you're in an input-driven mode. And you don't have any need to stabilize your intention until you're done. And you're adapting to that, and that significantly reduces cognitive control. People who do that a lot. Actually, I found out in a recent study that young people, adolescents, young adults are susceptible to addiction to that, and old people. So I have to watch it. And you might know, I know that some of I'm already a little old, but some of my older peers, some of them are very much always watching TV forever. And I just saw my mother-in-law were divorced, but I still visit them occasionally. She's 96 and she's a little dement, but she recognizes me always. She's very friendly. And she says, I was just saying in front of the TV. And I had to go in front of her, down, in Portuguese way, you kiss each other. And then she comes out from this world for a moment, and then she goes back and she's, no, it's just an intuition. I don't want to say this psychologically true. And so these are exceptional cases where you're so input driven, right? And there's enough stuff like that. And that's when you're very passive. Well, when you're sitting in front of your computer and YouTube is not on, then nothing happens unless you do something, right? And if you're just by yourself, a thought will come up and another thought and so on. And that's the So again, so when you're driving it yourself, the flux is in a sense from your mind. Every state creates the next state, right? You could think if you're just thinking, then the next thought comes because you had a previous thought, and that's done, and thoughts are competing, the next one comes up. And so that's all driven by the current state, the intentional state, and that's my word to mind. So action-like, may better say it's action-like, because you're intending a certain state. And the perception-like, and even the word is a bit misleading, right? Because true perception is also somewhat action-like. But just this passive form of perception, that would be where stuff from the outside drives things. It's essentially what the words of these shorts, or what they're called, these TikTok and these things, which then themselves also have very short in duration, and they always have a new initiation. Right? Something starts, and then so you have minimal cognition. You just need to say, should I click on it or not? I don't know actually how TikTok works, but in YouTube you have shorts. Some of you might not know that, and so I don't use it on the phone, but when I'm on a computer, they have a whole like tiles, and you can click on one. And the only thing is, which of the 5 one am I going to click on? And then, something. So that would be mind to world direction of it. Yeah. It's actually good then with your confusion. I see that this terminology, if you want to make it more understandable, we should talk about the flow and not about the direction of fit. Yeah. But that's a term that's established. That's why we took that. Yeah.
I just wanted to make a comment to this term itself, so how term uses it. So the idea is that he speaks about the conditions of an intention being correct.
Yes.
So it is perception, in which sense it is correct, when it feeds through the world. So it means it's not an illusion. That's why it's kind of like this. But when it's an intention, in which sense it's correct, okay, it's not correct, but it's like kind of being fulfilled. So in this sense,
yes, yeah, that's exactly where the term comes from. So the example of a mind to world direction of fit, that would be where the condition of satisfaction isn't trivial. From their point of view, would be hallucination. That's always the example they take, right? If you suddenly create an activation, but it does not correspond to something in the world, that would be a perceptual state, let's say. that is, that is not satisfied. And so that's see a little bit, we're a little odd to have these funny examples, right? It already shows that there isn't really much there. So this is really, so it's, yeah. So I only must say, I only recently became aware of how odd this is. We did this condition of satisfaction intention thing for a long time. This was 2010. So we've used this for all our sequence generation. And it was only in this project that we were forced to do both, right? Because we really want to make the agent autonomous. And that means it has to do all of those things. It also has to perceive, to build the world. So when it's not that busy, it will just take in the scene and store stuff and so on. And we had many versions of that, so now I no longer know exactly what happens, but in some versions of it, it would have all kinds of behavior going. Then the goal is set and so on. And so and then in hindsight, now look at that. Now that made us aware of how special those cases are and how more fundamental the other one is. That's sort of really the major insight from this work. I think I want to write a review chapter on that, because I think people will not get that from our paper, which is way too nerdy. Even though it was already much nerdier before, and I revised it, but now it's still way too technical. There's a second point that I usually have a whole lecture about, and this already got too many slides, so I just have it in one sentence here at the bottom, and that is, how it's possible to build these architectures. I don't think I talked about that here, right? So you have this huge architecture here, one of those pictures, let's say. So this is not even the whole architecture. And again, this only shows a subset of the stuff. And so when you did this little CEDA exercise, at least before, I don't know how far you got. You might notice you drag these things in, you connect them, and now you have to tune that, right? You have to tune that the peak comes up in the right field and makes a selection, or it works as working memory and so on. And so you have to ask yourself, so if I do that, like I make sure this is a field that represents color, and it's the working memory of color, and it's selective. It only has one peak at a time. And that's like you store the queue. You want to keep the queue, what you're looking for, in working memory, and only one queue at a time. And after you gave the queue, got it from somewhere else, let's say from a belief system, now you're looking for a yellow. You want to keep that yellow in some field. And that will work. You can tune that to be right? The interaction has to be right and so on. And now you build an architecture around that. This couples into other things, and other things couple into that. How do you know that still works? And in fact, sometimes it doesn't. When you build an architecture, then sometimes if you added more inputs to this field, suddenly it builds peaks all the time, or it makes, or it's totally inhibited because there's too much activation. And the theoretical reason why it works reasonably well is that it's attractors. So attractors are stable states, as you know, and that means that you can change the. So stable really just means that you can have all kinds of initial conditions and converge to them, right? That's what stability means, this convergence from all kinds of neighborhoods. Mathematically speaking, when you have a stable state, you are also structurally stable. There's a mathematical theorem that says that. And structurally stable means that if you change the equation a little bit, the solution will also just change a little bit. And giving an input is like changing the equation, right? Something outside the equation that now is like a term in the equation. So when you have an attractor, it guarantees that if you vary the equation and you give some new inputs, it will stay. Only mathematically, it's only infinitesimal. So it's a question. In practice, it's going to be some distance from the instability. So the fact that this attractors gives the system structural stability, and that gives it this robustness to retain its function, and the function is the dynamic regime, as you make a larger architecture. And it's not perfect because, you know, in practice, we're going more than infinitesimal, and sometimes we're going beyond the border, and when we have to retune the architecture. Right? So that is one reason why the architectures work, because they are robust under scaling this way. Now, I can imagine there's a whole sub-architecture that never gets activated under some conditions, but suddenly it gets, and then, you know, everything else could become unstable. And so this allows you to, in principle, solve that problem, even though there might be still some tuning problems. You might get epilepsy in this brain and stuff like that. The second point is a little bit more subtle. So this point is relevant in the network literature, in that most people argue that we don't use attractors. We're all just using transients. It's input driven, right? We're going from transient to transient in this picture. And they say, oh, these guys are with their attractors. Oh, this is like, there's an article by one of our competitors who says that that's wrong. And no, it's actually right. And they have not been able to build good architectures. The problem with this, the other picture, is the classical problem of the analog computer. The analog computer, unlike the digital computer, doesn't work well. That's why only the Soviets kept using it. It's because if one component of the computer is changed, everything else changes too. So it's very difficult to preserve its function. It's like a very difficult to tune thing. Anyone who has played with the quark synthesizer? No. I actually do that. That's really fun, and that's very unstable. Anyway, so that's one point. The other point is that we have some fields in here. Like I say, this is over color. And so it's over color by virtue of some connectivity that ultimately it gets input from the retinal surface that is about color through some path, right? That's sort of our thought. But when I make a big architecture, there are all kinds of inputs that are going around. So could it be that then under some other circumstances, it's not color that is represented here, it's orientation or, you know, movement or something else, right? And so that is actually due to it is true that this field is always about color only by virtue of the feed-forward connectivity in this system, both from the sensory surface to this field and to the motor surface. And so it would be possible to make a model like that, where sometimes it's color, sometimes it's pitch, or it's something else, right? We call this the non-synesthesia principle. Some of you might know synesthesia. Some people have that some people, when they hear a sound, they also see colors or feel colors or have smells and so on. It's usually considered a disorder. Some people use that for inspiration or something. And so it's not exactly clear what that is, some complicated thing. And so we just use this analogies. Non-synesthesia principle, that is, that we're actually saying only architectures that don't mix it up that way are realistic. So in your brain, you don't mix it up that way. And so that is an additional assumption. So it's a property of the brain that it isn't like that. We know that partly it is really genetically coded. That is when the brain grows in the embryo, it already has that property. So there have been attempts, some of you might know, of disturbing a brain, like taking the visual nerve into the auditory system and see surgically in an early phase, and then see if the auditory cortex can sort of develop visual cortex type properties. And so it's kind of an interesting story. It's mixed because somewhat, it can do that somewhat. And there will be some neurons that are tuned to visual array in the auditory cortex, but it's quite limited what it can do. So the learning process, that's experience-based, right? That's once some animals, I don't remember what kind of animal it was. When these young individuals get sensory inputs, then that's when they learn. But it has severe limitations in this whole topic of analyzing those. So the net result of that was to understand that the overall architecture of the brain is actually morphogenically specified by growth, not experience dependent. Some people call that genetically coded. That's just a word to say somehow these growth processes, what organizes them, but it's not experience that guides them. So it's not learning in that conventional sense, right? And so in a way, one could think that it's an evolutionary result that our brain has this particular property of not mixing up the different dimensions all the time, which makes functional sense, right? If you had that kind of confusion, you could imagine what kind of properties arise. That's significant because this kind of invariance is the central topic of modularity in classical information processing. In classical information processing, called encapsulation there, that every computation module has only the access to the inputs to the information that is given as inputs, and it gives certain things outside, and its inner states are not available to anyone else. It's called encapsulation. And this comes from computer science, and it's a principle in computer science just for good coding. In computer science, it's really that if it's a large piece of code and all kinds of programmers work on it, and people allow that some subroutine uses stuff elsewhere, makes assumptions about what's elsewhere, and that stuff is changed, then the code isn't going to work anymore. So to make it maintainable, they want that every module has a well-defined list of things it gets as input, and this it gets as output, and anything else is taboo. It cannot touch that. And there are programming languages that enforce that, right? And then theorists thought about the mind. Jerry Fodor, some of you know him, was made a big story about that and thought it was psychophysically real, and you could not cognitively penetrate certain things. That was the signature of that. And a whole kind of discourse about that can be criticized in its own set of issues. But it sort of reflects, this is not exactly the same, but one could say, well, this property of non-synesthesia, that you should keep your dimensions clean, could reflect similar sort of evolutionary pressures, that if those organisms who didn't do that had more trouble when they evolved, when they changed something, then things really can fail catastrophically. So these are essentially the two things that are needed. The dynamic modularity is this due to stability, and this non-synesthesia makes that the contents, the information, is somewhat consistent. And that is actually ultimately why we can scale these architectures. And so we meaning the guys working with attractors, we are the people who pull this off. So I mean, even though this agent is totally trivial and doing something stupid, you will not find any neurally inspired model that does anything like that and is really neural. Now, you have models that do fancy stuff, but it's an algorithm that uses some neural networks here and there. But to have something where it's really just the neural activation doing everything, that's unique. And these are the properties that make that possible. Good. That was more like claim to fame or something.